Welcome back. So in section 13.3, we're going to be talking about surface area. And our surface area is the total area of the external surfaces of a three-dimensional figure. So when I measure surface area, what I am measuring the surface area on is a three-dimensional figure like a cube or a box or a cylinder. But I'm measuring the external area, and so that area is it should be a two-dimensional measurement. Okay, so something in uh, with units like inches squared or feet squared or something like that. So in the most general example, we'll talk about we'll look at a prism, and so here, kind of a, a specific type of prism would be like a box. And I think the easiest way to measure surface area, kind of regardless of the shape, is to think about what the area would be if we disassembled that object. And we laid it out flat and we just calculated the total area that way. So this is kind of nice. It kind of builds on what we were doing at the end of last time. So with this, one of these last examples, we looked at this basketball key and we used both the area of a rectangle and a semicircle to get the total area of the key. And so we're going to want to, those techniques lend themselves nicely to computing surface area. So what I've done here is kind of drawn our box. It has a height of 3 by 5 by 8. And in this specific example, we're going to think of kind of cutting along these edges and disassembling our box. So this is a fun, easy experiment to actually do out with one of your Amazon purchases. And we're going to use the length measurements we have to get a bunch of areas. So I'll just label, so basically I want to take all of these little sections that the box is cut up into, and I want to find the area of each of these little sections, okay? And so the total area of this disassembled box is the area of A plus B plus C plus D plus E plus F. And let's see, from this picture, it's pretty easy to see that the area of A is just 8 times 3. Put it right here, 8 times 3. The area of B looks like 5 times 8. The area of C looks like 5 times 3, because this length will also be 3. The area of D will also be 5 times 3. The area of E is going to be 3 times 8. And finally, the area of F looks like 5 times 8. So multiplying this all out and adding it all up, we should get the total area of 158 inches squared. And I know my units are going to be inches squared on this because the area of each of these has the units inches squared, and then I'm just adding them all up. So, great. So this technique works all the time, especially if you're not aware of a general formula or the general formula, or you forgot it for some reason. This method works. And then, but how we basically get formulas for the surface area of our other more general figures is by using this idea. So so for a general prism, so if I don't have, like here at the top, I have a rectangle, but maybe I have a hexagon or a 6-sided figure, as opposed to a 4-sided figure. What I want to do is I want to find the area of that region. And I notice that I have two of those will make up my surface area, that when I disassemble, I have two of these areas. And then when I disassemble the rest, what I end up with is like a ginormous rectangle, right? And so the length of this rectangle will be the perimeter of whatever polygon this is. Um, that's what this P is. And then the width will be the height. Okay, so this is the height and this is the perimeter. So for my total surface area, I have 2 times the area of the top, and then I have the perimeter times h, which gives me the giant rectangle area. So that's the P times h corresponds to this whole region, and then the 2 times a corresponds to these two pieces. Okay, so basically I want to extend the same idea to other shapes that aren't necessarily prisms, so that don't necessarily have polygons on the top and the bottom. So for instance, a cylinder is very similar, but we don't have a polygon on the top, we have a circle. So we're going to basically use the same same kind of principle here, or the same idea, where I'm going to take the area of the top and bottom circles. So I should have 2 of those. And then I want to compute the area of this rectangle. Okay, so the surface area is 2 times those the area of the top and bottom circles, plus the height. But this time, instead of perimeter, we don't use the notion of perimeter for a circle, we use circumference. So this is going to be times the circumference. So basically the same exact formula as you can see that we had for the prism, but we're using circumference instead of formula, or sorry, instead of perimeter. And then, of course, since we know that these shapes are circles, we know formulas for the circumference and for the area. So both in terms of the radius. So let's say we have some radius r in this semicircle, then this is going to be 2 times pi r squared, since pi r squared is the area, and then plus h times the 2 pi r, since 2 pi r is the circumference. So simplifying this, or rewriting this formula a little bit, I can factor out a 2 pi and an r, and I would just be left with r plus h. So you can check that if that seems not clear to you. You can kind of check that algebraically. Okay, so great. So this comes from the same derivation basically that happens with the prism, just by unfolding our cylinder. And we can do a similar thing with the pyramid, but the pyramid is going to be a little bit different, right? We would expect our formula to be a bit different, just given the fact that, I think my screen is frozen. That's what's going on. There we go. Okay, so just given the fact that we don't have 2 copies of this polygon on the top and the bottom, right? We just have the one. So if I unfold this region, instead of having those 2 areas that I had before, notice I just have one of these. So for my surface area of my pyramid, I'm going to have just one of those areas. And then I need to find, to add, so that accounts for, let's see, this piece. But I also need to account for these other little triangles that come in here, right? And so what they do is we measure them as triangles, okay? So let's see, so we say, let's draw this, we want to find this height L, of each triangle, right? So that's what we normally were calling H. We're calling it L here because don't want to confuse it with like the height of the entire pyramid. So I'm basically just tracing it up the side of the pyramid. And then L times, let's call this B, would be the area, or sorry, 1/2 L times B would be the area of this one triangle, right? But I'm going to sum that up for every single one of these bases, right? So this should then be, instead of 1/2 L times B, it's going to be 1/2 L times P. So P, that perimeter, is saying I'm basically summing up each one of those bases. And that it gives me, that gives me the area of this whole region, as opposed to just one of the triangles. Okay, so for example, we have on the right over here, we have an example of a pyramid, and it's a pyramid with a square base here. And so what I want to do is I want to take the area of this square base and first find that area. And so that area is just 10 times 10, or 10 squared. And then I want to add up the area of these 4 triangles. So the area of the 4 triangles is going to be 1/2 the base times the height, which is 13. And then there are 4 of them. I'm doing this in a slightly different form than we had the derived formula in. The derived formula really looks like 1/2 times the perimeter, which was 10 times 4, right? 1, 2, 3, 4. So that should be 40 times the height. And you'll notice those are obviously the same numerically. Okay, and still having that area of 100. And simplifying this out, this should be 100 plus 260, which equals 360 square units. Great. Okay. So 2 more cases to look at here. So one example with a cone is, of course, very similar to what happens with the pyramid. In this case, again, we just have one of these areas because we don't, we only have one circle. We don't, unlike in the cylinder where we had one in the top and the bottom. So I don't need 2 of those, I just need 1. And then, of course, it's going to be 1/2, and we would expect it to be the length. And instead of the perimeter, it's going to be times the circumference. And then the only difference in this case is that we can use the fact that we know what the area and the circumference are in terms of this radius r. Okay. So the area, of course, is pi r squared for the area of the circle, and this is 1/2 L times the circumference of the circle, which is 2 pi r. Again, we could rewrite this a little bit if we like, and one way we can rewrite it. So a way that they rewrite it is in terms of, L being this length along the outside of the cone, they want to rewrite it in terms of the height of the cone, h. And so we can find the height of the cone h in terms of L and R, but by just using the Pythagorean theorem. And so that's what they do here. They use the fact that L squared plus R squared, oops, sorry, H squared plus R squared. H squared plus R squared is equal to L squared. And so if I were to solve, oh, and so that's solve for L, it's just the square root of H squared plus R squared. And so that we can get this in terms of the radius as well and just the height of the cone. Of course, it kind of matters what you have, but this is a nice version of this formula as well. So this is 1/2 then H squared plus R squared, the square root of H squared plus R squared times 2 pi R. And then there's just a little bit of simplification we can do by just, we have a 1/2 times 2 here, so we can rewrite this as pi R squared plus, if we want to move that pi R to the front and cancel the 1/2 and 2, we end up with this version of the formula. So of course, this is kind of a not very nice formula to memorize, but it does help to kind of know where these things come from. So to kind of see this motivation for the formula for the surface area. Last but not least, they give a formula for the surface area of a sphere. And I think that, as far as I can tell, your book does not give a derivation for this. I think that I think it would involve calculus to give a rigorous definition for the surface area of the sphere. But I think it was it in the beginning of the last chapter, I think? There was a note about Archimedes gave a really cool, found this cool relationship that the surface area and the volume of a sphere are both 2/3 the surface area and respectively the volume of a cylinder. And he found this out by, I think it was using some sort of weighted scale system, if I'm remembering correctly. But there's a really cool explanation of it in the front of, I think it was either this chapter 13 or maybe it was chapter 12. So regardless, we found that we have this really cool relationship between the surface area of the sphere and the surface area of the cylinder. And so we already know the surface area of the cylinder is just, so my surface area of my cylinder, we said above is 2 pi R times R plus H. And if we look at this sphere embedded into the cylinder in this way, the height of the cylinder is 2R. So if I do this substitution, let me move this up a little bit so I have a tiny bit more room. So if I do this substitution for H, the surface area of the cylinder is 2 pi R times R plus 2R, which is really 3R. And so that's 3R. So this is 6 pi, I think, R squared. And this would be the surface area of this blue cylinder. But now we want to find the surface area of the sphere, so we're going to multiply it by 2/3 on this whole thing by what Archimedes tells us. And what we get is 4 pi R squared is the surface area of the sphere. Okay, So just to point out here, there are a few exercises towards the end of this chapter. I think 19 and 20 are coming from part A there, if you're looking for them, of section 13.3. I really like 19 here. It says a square that's 6 centimeters on its side is rolled up into the form of a lateral surface of a right cylinder. What is the surface area of the cylinder? So kind of going backwards. Um, and let's see. And number 20 is really interesting too. So we say we have a sphere with a diameter of 10, and we want to find the surface area of the smallest cylinder that contains that sphere. So yeah, some interesting questions here that I would be happy to discuss with you in office hours or have you answer in office hours at any point. Great. And I'll see you next time.